now?
Yeah, I started recording actually. Yeah.
Okay, okay, good, good. So the next student is Chen Tong. He wanna talk about homotopy theory and fundamental theorem. Please, you can start.
Okay. Good afternoon, Dr. Dulip and Dr. Monia. I'm Chen Tong, and my title is Homotopy Theory and Fundamental Group. In this presentation, first I will recall on homotopy and fundamental group, which is what I present in last time. After that, we'll see campaign theorem, and lastly, we'll talk about covering spaces. Okay, homotopy. Homotopy is a tool to describe a path deformation to another path, and this deformation process must be continuous. So in mathematics, we use f to a function to describe a path and g is a path. And we say that if f can be deformate continuous to g, then we say that f and g are homotopic. And the next is homotopy class. If f and g are homotopic, then we collect them, and also the path that homotopic to f, and we collect together, then we put in a set, we call that homotopy class of f. And if f and g are not homotopic to each other, then they are from different class. Now is the fundamental group. Okay, in a space X, a point, we can see that we can construct some path, some loops inside the space, and we collect all the class of the loop together. Then the set is form a group with the operation is composite function. So this group is also called a fundamental group of X at base point X0. And this group is we denote by X1, Phi1 X X0. Note that this base point is not very important because we can change the base point. For example, I change to here. Then we can define a map beta h is change the base point from here to this point, and this map is isomorphism. So the group is still isomorphism, means they have same structure. Here is some examples of fundamental group. Okay, first one, let X be the convex subset of Rn. Then the fundamental group of X is trivial. Here, trivial means the group is only one element, which is the trivial one. So all of the loop is homotopic to the constant loop. The next example is Phi1 S1 is isomorphic to Z. These two examples we already seen in last time presentation. Okay, the third one is the wedge sum of two circles is the fundamental group is Z star Z. This one is the free group. Free group. A picture is like this. Maybe a base point is here. Then is either a generator is this circle and another is like this. So the free group is maybe something like let A be A. This one is A, and maybe here is B. So it's like A M B and A something B something something like this. If I use a vector to represent this, then something A I B I. Then these two these two got two generator and maybe A J B J. Then these two vector must be linearly independent. So the next example is Phi1 T. This T2 is the two-dimensional torus. The fundamental group is Z times Z. And later I will show how to compute this fundamental group using Van Kampen theorem. And another example is the fundamental group of real projective plane is Z mod 2. Van Kampen theorem. Let X be the topological space with path connected. That U will be open subspace of X such that the union of U and V is the whole space, and U intersect V is non-empty and path connected. Then we have this. Here, this one is the amalgamated free product. Okay. Okay, now we compute the fundamental group of two-dimensional torus using Van Kempen theorem. Pi1 t squared is z cross. Okay, first of all, we see that from this picture we can see that the torus can be drawn like this. Here the blue color is a loop going to the y-axis, and the red color is a loop goes to from x-axis. So in this picture we can see that we can look the structure of torus using a square. But before gluing them. So I draw the picture here. Now we apply Van Kempen theorem by this setting. Okay, for this, the blue color highlight we call it, let it be U, and the yellow color let it be V. So we can see that this part is the U intersect V, and this U intersect V is not empty and also path connected. Okay, we can see that this U is a circle. It's a circle, so this is a convex set. So the fundamental group of U is trivial. For V is if we draw in torus, it's a punctured torus. So you can see that this is the deformation of torus, and this four has same homotopy type. So a punctured torus is same homotopy type with the wedge sum of two circle, and the wedge sum of two circle is Z star with Z. This is a free group. Now we see the U intersect V. U intersect V is something like this. So for this red color, I make it more smaller, so it will become a circle. So this is the fundamental group of this is Z. Now we're using Van Kempen theorem. Pi1 U intersect V. Okay, this Pi1 U intersect V is Z is generated by 1, and the identity in Pi1 U is trivial, so it's just E, and a loop in V is like this, or V approach like this. First we go here. Here this one is A. I let it be A lah. And B. So a loop like this, it will become A, B, A inverse, B inverse. So loop will be A, B, A inverse, B inverse. From Van Kempen theorem, we need these two must be equal. So we have A, B, A inverse, B inverse equal is identity. So we have AB equals BA. So we have this line, and AB is the generator of loop in torus. So we get this group is Z cross Z. So we have the fundamental group of two-dimensional torus is Z times Z. Okay, now we see the covering space, homomorphism of fundamental group. Okay, in abstract algebra, we learned that if f x to y is homomorphism, then this is a function to describe the relation of between two groups. Now we see the homomorphism of fundamental group. So here F induce a homomorphism from Pi1 x to Pi1 y. So an element in this group actually is a class of loops. So this maps a loop in X to another loop in Y. Here is two proposition. Okay, let X, Y, Z be topological spaces. Suppose that we have F star map Pi1 x to Pi1 y, and G star maps Pi1 y to Pi1 z are homomorphism. Then the composition maps Pi1 x to Pi1 z. Means this function will map a loop in a loop in X to a loop in Z, and this also a homomorphism. And another proposition is the identity map. Obviously, this is a identity map, maps pi1 X to pi1 X, and this is called the identity homomorphism. There's another, it's called isomorphism. Okay. Now we see the definition of covering map. Let X and X title be topological space. We say that P map X title to X is a covering map if P is continuous and there's two following. For example, this is X title, this is X, then P maps this. Okay, the first one, for any X in P, the P inverse X is disjoint union of point. For example, this is X in this space, then the P inverse of X can be many. For example, something like this. The second is for any neighborhood of U, X, the inverse of this U neighborhood is also a neighborhood, and this neighborhood are disjoint. If there is a covering map X data title to X, then we say that X data, this one is a covering space, and here is two example of covering space. Okay, the first one is the easiest one is the trivial. Let P map X to X by defined by this Px equal to X. Then obviously this is satisfy these two conditions. So this is the trivial covering of X. Now we see the covering space of S1. Okay, let R map to S1. This is R. This is S1 defined by this exponential map E2 pi ix. Then this is this R is the covering space and this S1 is the base. So this map have a property that Px equal to X congruent to X mod 1. For example, here is 0, 1, 2, then if P, for example, P1.5 is here, so P1 in this S1 is go one times and half. So this is the covering. Okay, next one, the torus. Okay, this is the setup. Blue color is the y-axis and red color is the x-axis. Let P maps S1 to S1 defined by this PT equals to 2t, 3t, where t is in unit unit interval. So the image of this function is above, wraps the x 2 times and wrap the y-axis 3 times. So in this table, we can see that this 1, 2, 2 and y is 3, 1, 2, 3. So line is like this, and I maps to a torus, then I will get a loop in torus. So if I ignore the torus, means we make the torus vanish, then we can get a knot. This knot is also known as trefoil knot. If I change the number of these, 2 and 3, maybe I change to 4 and 5, then we get another torus knot. So here is some example of torus knot. Here is some example. Okay, now we see the proposition. Let x not be a fixed point in X and X not in, then the homomorphism is injective. Because I introduced a theorem is if here is the covering space, here is the base space. The fundamental group of the covering is the subgroup of the fundamental group of base space. And if there is a homomorphism map from this to this, then this map is injective. here is an example. If P maps R to S1 be a covering by this one exponential map, then we can see that in 0 this point, the loop in this space is something like this, go left and go right. After that, back to the 0 this point, then this is homotopic with the identity loop, the trivial loop. So the fundamental group in this space is only the trivial subgroup. So this is trivial subgroup of Z, and Z is the fundamental group of S1. If I set another function, another covering by this one, Pz, Pn map S1 to S1 defined by Pnz equals to Z power n. Here the n is the times of loop turns around the circle. So for example, n is equal to 1, then like this 1 times, then n equal to 2 in this circle, then turns 2 times. Okay. For this different n, the fundamental group is nz, which is the subgroup of Z. Means every different n will provide a different covering space of S1. So we can identify Pi1 X together with the subgroup of P star. In addition, the subgroup of this, if we choose any subgroup of this group, we can get we also can find a space that the fundamental group of the covering is the subgroup of this. If the space is good enough lah. Here we say that the space is good if the space is path connected, locally path connected, and semi-local path connected. Okay, now we see the number of sheets. The number of sheets is the cardinality of the set P inverse. Okay, I use back this example. Here got 1, 2, 3, 4, 5, 6, 7. So the sheet of this covering is 7. Okay, here is a proposition. Let X and X tether be path connected topological space. Then the index of a covering P is equal to the index of P star. Here is the way to get the index. Okay, now we see that transformation. Let Px map X theta to X be a covering. That transformation is a homomorphism. Map X theta to X such that this diagram commutes, and we have P equals to P composite with F. Okay, let's see an example so we can understand this more. Let Fk maps R to S1 defined by Fkt equals to exponential 2 pi I kt. So here this k actually is the maps k times around the circle. So we can see that for each k we will get different covering space. If we collect all the covering space, we collect all the map Fk, k goes for any integer, and we give a operation for any function, and we compose it with it, we will get another function, something like f n composite f n is ref m plus n. So we also one of the fk. So this is isomorphic to Z. I mean this group. So this is the deck transformation of this covering. So we have that P is isomorphic to Z. Now we see the universal covering. Let P1 maps X tilde 1 and P2 X tilde 2 to be covering space. And we say that P1 is a universal covering space if there exists a unique determined homomorphism such that this diagram commutes. The way to understand this is this one is the base I1 and the covering. Okay, for each this group we can find each subgroup, but the universal covering is the group such that this one is only it is equal to the trivial subgroup. Okay. here we can see that from example just now, you can see that for the covering of S1, the trivial subgroup of this Taiwan S1 is Z, and the trivial subgroup of Z is only the trivial subgroup, and the covering of this group is the real line R. And another example is the universal covering of the RP2 is the S2 sphere. And we have another example is the torus. Universal covering of the torus is a plane, maybe something like this. Okay, thank you. That's all my presentation.
So thank you for your presentation. And Julie, please, if you have some question or comment.
No, actually, it's really nice. I mean, it's a very nice presentation. So did you, try to think about like, higher fundamental groups? I mean, I know it is like, if you're interested in, yes.
Pi 2, Pi 3, that one.
Yeah, like kind
Yes.
of,
I haven't started to learn that.
Okay.
I didn't teach him about this, but
no, I know.
I think there is another student that I already taught him about. This is what we call loop of a loop. You know,
okay.
For example, the sphere S2 is a loop of a loop. We can see this geometrically. Geometrically, the sphere is a succession of loops. So it's a loop of a loop. And pi 3, I mean the third, will be a loop of a loop of a loop, and so on. And this is, I think it will be the project of next project, maybe this for next semester or something.
Yeah. I mean, this is quite a lot, so it looks like
I have my, it will be my next proposal is the loop of the loop and the loop of the loop of the loop and so on. I mean, the generalization of the homotopy. This is known, this is known, but it becomes more complicated. But at least for the loop of the loop is not complicated. I mean, for pi 2 is not very complicated. You can see this easily. For me and you easily, but for student I think is. But anyway, okay. So yes, if you have some question, you can ask or.
No, I mean, yeah. So it's just curious because he made a good progress. I mean, very nice. I mean, thanks for the presentation.
Excellent. So, yes. Yeah. Thank you so much for your presentation, and so you can stop.